Recording in progress.
None of the methods in operations research is so simple, and these methods are, all of these methods look to you very tedious. I mean, yes, it's true that I'm saying I'm not going to apply simplex method because it is tedious in this particular case, but the method that I'm going to show you right now, and since you will be doing it for the first time, to you that also may seem to be very tedious. Okay, well, tediousness will always be there, remember, because it is operations research problems. These are operations research problem, and in operations research, what happens, the methods are algorithmic based methods, and therefore every method has its own time span, so you have to bear with that. But when I'm saying that this method is, the method that I'm going to describe is better than simplex in this particular case, that means I'm comparing the tediousness of two tedious methods, comparison between two tedious methods. And that is that the method that I'm going to apply over here right now, it is better than simplex method for the current situation. Do you have any idea what sort of method? Have you ever heard of this? I don't know whether you have any idea or not. What method I'm going to apply over here? Can you tell me the name of that method? Or you always can you can take the help of Google, but I'm not asking you to Google to help to take the help from there. I'm asking, just I'm trying to know that whether you have heard of it or not earlier anywhere. The name of the method that I'm going to apply over here right now. Probably not. The method that I'm going to apply is called Hungarian method. It's not like that the method has been has originated in Hungary. The Hungarian is the name of a person. I do not know whether it is his surname or first name, but it's the name of a person who has deduced the method. It's called Hungarian method. And the most important part is that, and this is very important for MCQ also, this method is applicable only when we deal with minimization type of problem. Simplex method, the simplex algorithm that we discussed, was only applicable to maximization type of problems. And what would happen when we get a minimization type of problem in simplex method? We convert the problem into maximization type. I do not know, I cannot remember whether I showed you the conversion or not. If not, then later you remind me that I'll show you the conversion process. Here also, the Hungarian method, which is actually typically designed for minimization type of problems, can deal with maximization type of problem only when the maximization type of problems are converted to minimization type of problem in some way. Otherwise, directly you cannot apply Hungarian method to any maximization type of problem. But since my problem is having times as the matrix elements, then therefore we are in a position to apply Hungarian method to the given matrix. Now I'm going to discuss the steps. Step number 1. Construct a matrix. Construct a matrix in the following way. Okay. Consider the first row, select the minimum element of that row subtract that minimum from all the other elements of that row, including itself. Repeat the process for the remaining rows and do until all the rows are exhausted in the given manner. So I am going to, by using that rule, I am going to design a new matrix applying this step 1. Okay, below over here I'm writing. So I'm going to apply this operation that I have described over here in step number 1. I'm naming this operation as row operation. So after row operation, what would I get from the given matrix? Row operation. Okay, I'm writing it over here. You are supposed to write the headings each time you construct the matrix. I mean tasks, Roman 1, 2, 3, 4, everything you are supposed to write each time you do the thing. But here to just save the time, I'm not writing the column headings and row headings, and I'm just going to write the values. Okay, so first of all, let me consider the row 1 as has been told in step number 1. In row 1, the minimum matrix minimum value present in row 1 is 11. Let's circle it. In row 2, the minimum value is how much? It is 13. In row 3, the minimum value is 15. And in row 4, the minimum value is 10. So I have encircled all the minimum values in the given rows. I'm going to apply step number 1. This particular minimum element will be subtracted from every other element of the given row. So we'll get 18 minus 11, that means 7. Then that would be 26 minus 11, it is 15. Then this would be 6, and that would be 0.
Sir,
Yes,
sir,
yes, yes.
can you please repeat again? How can you draw the matrix 11 minus 8, 18 minus 11? I can't understand. 11 is the minimum form, and why we take 18?
No, I mean you have to construct the matrix now. So when you construct the matrix elements, the size of the matrix elements will be reduced. Now you are actually fixing the minimum element of a particular row. You are going to subtract that minimum element from every other element present in that row, including that minimum element itself, according to the step 1 of the Hungarian method. Now I have to repeat the process for each and every row until all rows are exhausted. Now for
okay, sir, understand. Now I understand that.
Yes. So in my in the first row, the minimum, I have to save time, I have just first of all written down all the minimum elements present in each and every row. I have started with the first row. First row, the minimum element is 11. I am going to subtract the minimum element 11 from every other element. So 18 minus 11 gives me 7. 26 minus 11 gives me 15. 17 minus 11 gives me 6. 11 minus 11 gives me 0. And this I'm getting by considering the row operation described in step number 1. Similarly, in the second row, since I have to repeat the process for every row, let's go to the second row. In second row, the minimum is 13. And so I'm writing here 0 because 13 minus 13 is 0. 28 minus 13 means 15. 14 minus 13 means 1. 26 minus 13 means 13. This is happening for the second row by step number 1. Now go to third row. Third row, the minimum is 15. So 15 minus 15 is 0. 18 minus 15 is 3. 19 minus 15 is 4. And 38 minus 15 is 23. And then come to the next one, that is last one. 10 minus 10 is 0. 24 minus 10 is 14. 26 minus 10 is 16. 19 minus 10 is 9. And here I'm going to write the column headings, Roman 1, 2, 3, 4. And here I'm going to write the row headings, which are subordinates. This is my step number 1. My step number 1 is done. Next, I'm going to write step number 2. Step number 2 is another construction of a matrix from the matrix obtained from step 1. Okay, not from the original matrix. Original matrix is now changed. The new matrix is this one. This is my new matrix. So from this matrix, I'm going to construct another matrix by some operation. The operation is similar to operation described in step 1. Except that these will be applied for rows. These will be applied for rows. Sorry. My mistake. Columns. This will be applied for columns. So I am not writing all the sentences that I have already written in step number 1. I'm just writing that, okay, from the new matrix that we have already got, I'm going to construct another matrix where by performing the same sort of operation that I have already applied for in the original one. But in this case, right now, I'm going to do it column wise. Previously, we did it in a row wise fashion. Now I'm going to do the same thing in a column wise fashion. This is the only difference that is going to be applied over here. So if I look at the matrix in column wise, you see the minimum in this particular first column, and that would, you know already that would be repeated for each and every column. So let's stick to the first column. In the first column, the minimum element is 0. So we are going to encircle it. This is my minimum element. In the second column, the minimum element is 4. In the third column, the minimum element is 1. And in the fourth column, the minimum element is any of the zeros. Any of the zeros is the minimum element. Okay, so basically, if I try to construct, and this operation that I have described here, let us name this operation as column operations. Column operations. So after column operation, let's see what we get. So for the first column, you see the things will not change, because since 0 is the minimum, so we will get 7 minus 0, which is 7, 0 minus 0, that is 0, 23 minus 0 is 23, 9 minus 0 is 9. For the second column, some elements will be, the elements will be changed, because here the minimum element is not 0. So the minimum element is 4. So it would be 15 minus 4, that is 11. 15 minus 4, that is 11. 4 minus 4 is 0. 16 minus 4 is 12. For the third one, we have 6 minus 1, that is 5. 1 minus 1, that is 0. 3 minus 1, that is 2. And 14 minus 3, that is 11. And for the last one, the column will not change, because the minimum element was 0 and 0. And let me put the column headings. This is Roman 1, Roman 2, Roman 3, Roman 4. Subordinate headings 1, 2, 3, 4. This is my new matrix. Basic purpose of this particular methodology is to bring as many zeros as we can into the picture. Okay, so in the original matrix, there were no zeros. Now we are getting lots of zeros in the given matrix. Okay, and it is a good sign. If I can bring as many,
sir,
yes, tell me.
স্যার ওই থার্ড কলামে স্যার ওটা লাস্টেরটা 13 হবে স্যার, 14 minus 1 13
Oh,
স্যার।
sorry. My mistake. Sorry. Thank you so much. It is 13. Okay, I wrote it 14 minus 3. Sorry. Thank you. 14 minus 1, that is 13. Now, as many zeros as we can get, that is our basic objective, and it is a good sign for the problem also. After this, and if you are lucky enough, I don't know whether I'll be lucky in this for this particular problem, but if we are lucky enough, then next step is going to give me the solution. If we are unlucky, then it would not be giving us solution. We have to do something else further. So can I go to the next page?
Yes, sir.
Okay, so in step number 3, I'm going to write how to make assignment. How to make assignment in the given matrix. If I am lucky, then I will get the assignment. I will get my solution in this particular step. But that will not imply that step 1, step 2, step 3 are the only steps of Hungarian method. I will be unlucky for this. If
this the name is the assignment method, no?
Assignment method or Hungarian method? Hungarian method for solving assignment problem. 2 names. Assignment method is, there is only one assignment method in operation research, and that is Hungarian. No other assignment methods are there. So it would be better if you call it as Hungarian method and not assignment method. Now listen to me carefully. I have so far applied 2 steps, step 1 and step 2. Now in step 3, I expect to get the possible assignments validating the mathematical model. If I get the assignment in this particular step, the desired assignment in this particular step, I would be lucky at the same time and unlucky as well. Lucky because my problem is done. Unlucky because, yeah, the problem is done, but probably the students will think that these are the, oh my God, this is the only 3 steps are there, and no more, we don't have to figure out other things. It is not going to happen for other problems. I have to then select some other problem. I have to start from scratch so that I shouldn't get any assignment at step number 3. Okay, because Hungarian method has many other steps, and that only can be shown if my step number 3 fails to give me the desired assignment. So first of all, let us see how to make the assignments. Okay, after step number 2. So I'm writing here in the final matrix, in the previous matrix, not final matrix, the previous matrix, or it would be better if I write in the current matrix. In the current matrix, try to find a row or a column which contains 1 and only 1 0. In the previous matrix, try to find a row or a column which contains 1 and only 1 0. Assign this 0, that is, keep inside a square box. If any other 0 zeros appear in the row or column containing this assigned 0, those zeros must be striked out. Those zeros must be striked out. Repeat the process until and unless you get assignments in every row and every column as desired from the mathematical model of assignment problem. This is my step number 3. Write it. Once you are done, you just tell me and I'll go back to the previous page. The important part in this particular paragraph is this one. Assign this 0, keep it inside a square box. I'll let you know how to do it. If any other zeros appear in the row or column containing the assigned 0, those zeros must be striked out. I'm writing the steps in my own way, my own sentences. In the book, the languages are more refined, in a refined way they do it. Okay, so probably I don't know how it is written in the book, but if you're starting from the book, then probably you may get some other types of lines. which may not be understandable to you, but you stick to only one particular methodology, try to apply it in different methods. Okay, you can stick to the book's methodology or to my methodologies, but try to be fixed to only one methodology. Don't study from here and there. But solution, the final answer will be same, whether we apply in the following manner or the book manner. So done. Can I go back to the previous page?
Yes, sir.
Now let us try to apply. Now they are asking me to find out a row or a column which contains one and only 1 0. Okay. So we start looking from, we'll first scan the matrix row wise. If no such row are there which fulfills my expectation, then we'll scan the matrix column wise. Okay, so I'm now going to scan the matrix row wise. So first of all, scanning row wise. Don't write it. I'm just writing for your understanding. Scanning row wise right now. In row wise scanning, what I'm going to see is that the first row, there is one and only 1 0. In this row, only 1 0 is present. As soon as I receive it, I'm going to assign this 0 by putting it inside a square box like this. This 0 is assigned. That means this particular place is occupied. That means I'm going to assign subordinate 1 to job 4. For subordinate 1 has got his job. Okay. And in the step number 3, it is written that if in this particular matrix, in this particular column or the row which contains the assigned 0, any other 0 is present, strike it out. Now you see, in this particular row, no other 0 is present. Only 1 0, row wise, if I look at it, only 1 0 is there and that is assigned. But if I look at it column wise, okay, then I can see that 2 more zeros are present in this particular column. So I'm going to strike those zeros. Because why? Because by the mathematical model, one particular column can contain one and only 1 0. One particular row can contain one and only 1 0. So these zeros must be striked out. Okay. Now next, come to the second row. Second row contains 2 zeros. But my step number 3 is saying that you are supposed to find out a row which contains one and only 1 0. So second row is not fulfilling the desired criteria. Okay. Come to the third row. Third row contains only 1 0. So we are assigning this 0. And in this 0, do it by green color. And in this 0, in this particular column, there are no other zeros. Okay, so we don't have to worry much. In this particular row, there are no zeros. 1 0 was there, but it has already been striked out. So we don't have to worry. This part assigning this 0 to means that the subordinate 3 has got his job, his task, and that is task Roman 2. Now, in the fourth row, come to the fourth row, no zeros are present. Okay, no problem. Let us scan it column wise now. Because we have to do it until and unless either all the zeros are assigned or striked out. Okay. Once all the zeros are assigned or striked out, then I can finish the task. Column wise, I can see that in this particular column, first column, there is one and only 1 0. Immediately we will assign it. And in this row, we can get another 0 which is present. But since this row has got its assignment, I'm going to strike this particular 0 out. And you see at this stage, we are left with no zeros at all in the given matrix. All the zeros are either assigned or striked out, and my job is done. All
Sir,
the
can you repeat this step once more of assigning the zeros?
Yeah, sure.
Yes, sir, please once more.
I have got the assignment so far. I have got 2 assignments. One assignment is row 1, and one assignment is in row 3. Now, how long shall we apply the assignments? Doing these assignments, the steps asks me to repeat the process until we get all the zeros either assigned or striked out. I can see in the matrix 2 more zeros are left. They are neither assigned nor striked out. So I have to repeat step 3 for these zeros, but I have to manage them. I cannot manage them row wise, because if I look at these zeros row wise from the perspective of the second row, a second row contains 2 zeros, and I am supposed to find out one and only one zero, which contains, I'm supposed to find out a row or a column which contains one and only one zero. But from perspective of row 2, I'm not getting it. Row 4 doesn't have any zero at all. So I'm going to do my scanning column wise now. So if I look at the columns, I can start from right hand side of the matrix. I can first start looking at column number by putting it inside a box. But the criteria of the mathematical model says that a particular row or a particular column can get one and only one zero assigned. Any other zero present in that row or that column will be striked out. Now, since row 2 has now got, from the perspective of column, row 2, from the perspective of column 1, row 2 has got its assignment here, and in this column 1, there are no other zeros, no problem. But if we see the assigned zero from the perspective of row 2, once again, in this row, one another zero is still there, which has not been assigned or which has not been striked out. But a particular row cannot contain more than one assignment. It means that you are assigning the subordinate to do 2 jobs at a time, task 1 and task 3. It should not be. One person can do only 1 job at a time. So any other non-assigned zero in that particular row or column needs to be striked out, and therefore we'll strike out this zero. And now if I look at the table, I see that if I look at the matrix, I see that all the zeros are either striked out or assigned, and no other zero is left. And therefore I can stop my step number 3 at this stage. My step number 3 is done. What is the outcome of this step? The outcome of this step is the following. If you ask me whether I got my whether I have got my solution matrix or not, the answer is no, I have not got my solution matrix. And why is it so? It is because according to the formula or characteristics of mathematical model of the assignment problem, each row must get one and only one assignment. But I can find out row 4, which has not got any assignment at all. Since the order of the matrix is 4, so my desired number of assignment is 4. But instead of getting 4 assignment, I have got only 3 assignments. And that implies that my job is not yet done. My problem is not yet finished. Lots of other things needs to be done to ultimately reach at the solution of the given matrix. What I am doing right now, I'm just copying the last matrix so that I should not lose it. Otherwise, I'll not be able to finish it, because I have to take your help then otherwise. So I'm just copying the final matrix that I have got and the sort of assignment that I have managed to get in this particular problem so far. So what am I saying? The assignment matrix, the characteristics of the assignment problem says that if the order of the matrix, we always need to have a square matrix. If the order of the square matrix is n, the number of assignment must be n. If the number of assignment is not n, my job is not done. Here I am got 3 assignments instead of 4, but I expect to get 4 assignments. But up to step number 3 is not able to give me 4 assignments at this stage, and therefore we need to do something further to reach to the optimality of the given matrix. So it is a good sign. It is a bad sign that my job I yet to be finished. Good sign because with this particular problem, I will be able to show you other steps, further steps of Hungarian method. Otherwise, I would have to look for some other problems to do the thing. Okay, so it's a good sign. Sometimes it happens that for a given matrix, step number 3 gives me all the desired assignments. All the rows and all the columns get their desired assignment. Sometimes it happens also. So you should not be panicked. Okay, 3 নম্বর স্টেপে আমি কি করে পেয়ে গেলাম অ্যাসাইনমেন্ট তো সব পেয়ে গেলাম, তাহলে কি আমাকে অন্য স্টেপগুলো করতে হবে না? No. If I get all the assignments in the 3rd step itself, we have to stop it, right? Stop there right now. But since I have not got my desired assignment, I have to proceed further. So I think that I probably my today's time is over. Do I have time, more time for today's class? Otherwise we will continue in the next week.
না স্যার, এটা আজই শেষ করে দিন স্যার প্লিজ।
শেষ করে দেবো, তাহলে তো নেক্সট সেশনে জয়েন করতে হবে, আরেকটা সেশনে জয়েন করতে হবে। এটা তো শেষ, আমার সেশনটা এন্ড হয়ে যাবে। তো তোমরা জয়েন করো তাহলে আরেকটা সেশনে, আমি শেষ করে দেবো আজকে এটা।